Our next breakout session is Next Generation Nuclear with Dan Buman. Dan is NPPD's Special Assistant to the Site Vice President at Cooper Nuclear Station. We've all known Dan was always special, but he's got it in his title now, so I think I'm going to do that next time I get a new job, is put special in front of it. Dan's an electrical engineer from the University of Nebraska, also has an executive MBA from University of Nebraska at Omaha. Started with the district in 1987, has had various roles in leadership up until now. So he's done a lot of good things for the district, all nuclear related. Dan and I actually used to work together starting about 1989, not 1890, 1889. For about 5 years, along with Todd Dern and maybe a couple others in the room here too. So I'm pretty sure we both had the same haircut back then too. So with that, Mr. Buman.
Thanks, John. You're right. We did have the same haircut, but you really got to stop being so bitter about not having to mature into an eye candy like I did. So I think they're laughing at you.
I'm used to that too.
Good afternoon. We're talking about next generation nuclear. You may hear a topic, hear a lot of different things that referred to: small modular reactor, advanced nuclear, next generation nuclear. They're all talking about the same thing. They're talking about changes that have gone through, taking what we've learned about nuclear power over the last 50-some years and starting to apply it and looking at new ways to be able to solve new problems. So we're going to talk specifically about next generation nuclear, but we're going to talk a little bit about some of the technologies to give you an idea. And then we're going to spend an awful lot of time about some of the exciting things that are going on right now, which is siting studies going on actively at this particular time frame in Nebraska, and what we're doing to look to be able to site the next generation nuclear. So when we look at conventional nuclear, when you think about that, and one of the reasons why we've gone and we've made some of these changes is conventional nuclear. You look at the Vogtle plants as an example that just recently came online. They were originally going to be about a $4 billion with a B project for the two of them. Because of delays that extended out, took 6 years over the time frame, took a total of 19 years of construction. Whole lot of different things that went on. It's a mega project that goes, and obviously that can bring in a lot of risks during construction. So what we look at is, those at 1,100 megawatts taking 17 years, and then the price going and increasing up from the original concept they had at 4. When they started construction, they said it was going to be 14 billion, and then the last numbers that we've seen has been around about 34 billion. That's a lot of risk of going forward. So based on that, we're trying to find ways to be able to reduce some of that risk in construction and licensing, being able to get those done. So one of the areas is something that's called small modular reactors. Small modular reactors is the next generation. It is an advanced nuclear. But again, typically the only thing that I'm going to characterize it by is basically the size. So instead of a large 1,200 megawatt unit, you're looking at building them in 300 megawatts. And you say, well, why would that make any difference? Well, first of all, you don't have to have a huge mega construction project going. They come in and a lot of the material is built in a factory and shipped, and so it can be assembled. And so they're working on this so we've taken, it has a promise to simplify the construction, dramatically reduce costs, both for construction and also for operating, because again, at a smaller unit, you don't have to have as many personnel on site. You still have a fair size that's in there, and shorten the construction time. By making them smaller, they've also been able to build in passive safety systems. So everybody always wants to know, is it safe? And I go back to Cooper Nuclear Station, has operated safely for over 50 years, continues to do so. The reason it is because we have the pumps and valves and ways of putting water on in that if something were to happen, we would be able to make sure that the core is always cooled and adequately maintained. To do that, we need electricity, so we have 5 different power lines coming in. But in the event that those all went on down, we have the capability of an emergency diesel generator to be able to pump, be able to fire up automatically and pump that in. In the event that one doesn't work, we have a second safety-related diesel. In the event that doesn't work, we have another one. So we have layers upon layers that we've built into these. By building these into passive, I no longer have to have all these pumps to force water in, to push that in. I rely on passive systems. I rely on 2 basic physics rules. 1, hot air rises, and 2, gravity always wins. And so as long as you have those 2 things, that's what the safety systems are. So now instead of having an emergency diesel generator that drives the cost of construction up dramatically, we've reduced down the size of the nuclear island. Just as safe, it's just been able to take some of that margin and put them more into the passive systems such that we're always going to be able to, just like what we can do today, we'll be able to do with these to be able to maintain all of them being cooled. Again, we talked about the factory built versus a mega construction site. We also, by doing this in this fashion, can standardize the design, quickly move from first of a kind sort of thing where you're going to see the costs up to eventually, second of a kind, to a third of a kind, to eventually an nth of a kind. And when you get to the nth of a kind, you have a predictable construction time, predictable construction budget, and predictable costs as you go forward. One other advantage that these smaller modular reactors have is that they are more flexible, so we have increased flexibility in operation. Obviously, since they're smaller, bringing a 300 megawatt unit on is a little bit different than bringing on a 800 or a 1200 megawatt unit. So again, it gives you a little bit more flexibility, but many of these different generations, as we start talking about some of the advanced nuclear, and we'll get into some of these details, actually have built-in other methods. Some of them are able to load follow, be able to very rapidly move up and down. Some of them have built-in thermal storage to be able to match intermittent generation. And so what you can do is you can basically ramp up at times to 150%. For example, if you looked at TerraPower that's being built out in Wyoming, they have thermal storage into molten salt that they're actually building that in so that they can put out 150% during time frames when they need it, and then cycling down to 50% and basically going in there. It becomes basically a thermal battery. And so with that comes a very rapid recharge with that also. So instead of spending a day of a recharge on a battery system, it actually is able to go in and recharge in a matter of hours. So you can have multiple cycles, during a day to be able to fill in if you have this thermal battery. All of that, like I said, better able to match up with what we're currently seeing in the grid with the intermittent forms of generation, pairs very well then with wind and with solar and other renewables. Of course, it is carbon-free, just like wind and solar. And again, it's what our customers have been asking for. And while the nuclear plants, the reactors themselves have been operating, have many years of experience, so they are a proven technology. They have not yet been demonstrated at scale. And so we're going to kind of talk about that. And so that's the one caveat that I'm going to put out there, that we still have to be able to prove yet. We have to prove its case as we're going forward, and that's where we're in. But we don't want to wait until it's all proven. Otherwise, we'll be waiting for quite some time. We'll talk about that a little bit here. So to give you some sort of idea of the sizes, so we can range anywhere from, with these advanced reactors, they can go anywhere from what they call microreactors. They're in the 1 megawatt to 20 megawatt. They're actually being proposed as being mobile, to be able to power at, for example, remote Department of Defense bases up in Alaska, various different places, being able to provide a power source that basically is mobile. From a utility and from a grid standpoint, it's probably not as valuable for us at this particular time frame, just based on the cost per megawatt that you would end up seeing. But again, if you have an application where you're like some of the defense places in Alaska, Canada is looking at this in several different areas also. It becomes a valuable place. You're no longer having to truck a lot of diesel fuel or anything else up to it. You can bring this in and they'd be able to provide not only the electricity, but can also provide heat, from to a district energy program there. Small modulars are typically considered to be something less than 300 megawatts, so they've just kind of naturally gone to about the 20 to 300 megawatt range. Variety of different types out there. We'll talk about a few of them. But again, they are targeted towards the smaller end, being able to put something in, be able to reduce the construction time. Instead of a standard construction time at a regular plant of being in the 5 to 7 years, they're talking about bringing them in 24 to 36 months construction time. And then they also range all the way up to full scale range, so 300 to 1,000 plus. So the 2 units that I actually started in Georgia are actually next generation nuclear. They are what they call a Gen 3/Gen 3 plus. They have a lot of the same passive safety systems, but again, because of some of the construction and some of the other risks, learning how to go and manage that is something that we have to be able to work our way through. So to give you some sort of idea of some of the versatility that this has, you look over on the left-hand side, you see what they call a microreactor. That one is not one that's on a truck, but again, they actually show Oklo. Oklo has a rather unique, they started off saying that they were going to be less than 1 megawatt, but they're going to offer them all the way up to 50 megawatts, be able to come in and work from a PPA standpoint to be able to just generate power. These are completely air-cooled, require no water. So again, you see that. You go over to the next one, which has LWR, which is light water reactor. Light water is just normal water. If we just said normal water, that wouldn't be as exciting as light water. So we've used the term light water reactor. What you're seeing there is actually one from NuScale. They're the ones that have actually gotten the design certification through the NRC. They're the farthest along from the licensing standpoint, but there's a lot of others that are coming in. All of the existing nuclear plants in the United States, commercial nuclear plants, in the United States are all light water reactors. So that's Cooper, Fort Calhoun was. They typically come in what they call BWR, boiling water reactor, or PWR, pressurized water reactor. This now expands this on out. So NuScale is basically a pressurized water reactor. GE has a BWRX 300 that they're coming in there. They use a lot of the same licensing techniques for some of their advanced reactors that they've already been able to do. They're able to bring that on. They believe they'll have them up and have it running and having the first one online. Actually, it's going to be probably up in Canada. They're targeting having it online commercial operation in 2028. Beyond just the light water reactors, because they're very good for making electricity, there's a lot of need for the heat coming out of some of these reactors for various industrial processes and also to be able to make more efficient generation. So they have other methods of cooling the reactor, and that's the only difference that you have. So you could substitute the water. Instead of keeping the core cool with water, they can keep them cool with high temperature gas. So you have high temperature gas. This happens to be X-Energy. It's currently in development. They're looking at pairing with Dow Chemical. Dow Chemical really isn't looking for the electricity. They're looking for the heat. They're wanting to be able to take that heat and be able to use that in their chemical processes down there. And they're looking at putting that in. Again, it has a it has an even smaller footprint. So water, when you start raising temperatures up in water, pressure goes up. As the pressure goes up, pressure vessel has to get thicker and thicker and thicker. High temperature gas reactors are operating at a much lower pressure. So therefore, they don't have to have these heavy constructions. And again, looking at reducing of costs, being able to go through the X-Energy has the capability to be able to ramp up and down fairly quickly. They can basically do, they believe that they can match the needs that plants could be able to operate in the real-time market. Again, not yet been demonstrated, but that's what they're targeting towards. Instead of using the high temperature gas, what can be used is liquid metal. So we've talked a little bit about Natrium or TerraPower, the one that's over in Wyoming, that's Bill Gates's. They use basically sodium cooled reactor. It's a fast reactor. It has an added advantage that they actually will able to be used to take some of the used fuel that we currently have that we're storing at sites and be able to take some of that and use that in their fuel stream. So it helps them out. The other advantage is that they get much, much higher temperatures than even with the high temperature gas. And again, when they're operating at basically about 20 pounds pressure inside the core. So you don't have this large pressure vessel once again. And then other molten salt reactors like terrestrial, various different items. Pairing into this one with TerraPower, they actually use liquid sodium to cool the core. They go through a heat exchanger. They go into a molten salt storage facility, very similar to what they've done with some concentrated solar storage. And they put that temperature in. So they're able to take the plant and they're able to run the nuclear plant at 100% power continuously. And when generation or the load is not as high as what the generation is, they're able to actually store that energy. So that's where the thermal storage pieces are coming on in. So all these different items, there's an awful lot of excitement going on. And the reason is because there's an awful lot of money floating around demonstration projects. There are over 30 demonstration projects across North America. They're slated to come online, go commercial between 2028 and 2032. So you're seeing an awful lot of activity going on in various different areas. There was several of them that are going to be over about 20 of them that are scheduled to come on by before 2030. The problem is if you're going to wait until that particular time frame to make a decision, at that particular point, obviously you're avoiding the risks of being first of a kind. You don't want to have serial number 1, but you're probably going to be somewhere in serial number 10,000 and you're going to have facing supply chain. So you got to be able to poise yourself to be a early adopter. So one of the things that the legislature had is they had foresight to actually put in a bill to do a small modular reactor siting study, looking at where in the state could we put the next small modular reactor. So they allocated $1 million. We've broken that on down. One of the requirements was you had to be a nuclear operator in the state of Nebraska, operating in the state of Nebraska, to be able to do the study, to qualify for it. So that's why NPPD is doing it. It is not an NPPD study. It is a statewide study. So we are looking across the state, looking all different areas in there. We did put a focus on existing generation facilities. So all existing generation facilities were included in there. This was not looking at trying to replace anything. But obviously, as you gain, there will be a end of life for all these plants, including Cooper Nuclear Station. It would seem to make sense that you would at least have some of this initial information that would be in there. Basically, the way that this was all done is we broke up the state into 6 different regions, and then made sure that there was representation in all of the different areas. I'm not going to go into a lot of the technical details, but they looked at where they basically broke it up and said, okay, is there any sort of 2 different terms that the NRC uses? Avoidance areas and exclusionary areas. Exclusionary areas, you would not want to put a plant in there. We did not identify any exclusion areas. We did identify some avoidance areas. Doesn't mean you can't put a plant there. It means you have to do additional work. And so based on that, the team, the engineering firm, looked at total of 32 different sites across the state. And from that, based on that, we went through what was called a phase 1, which was basically a desktop application. The reason that was all being done is you don't really want to have people coming out and going and kind of poking around and seeing a strange pickup truck in a rural Nebraska and saying, what's going on? And you say, well, we're looking at putting a nuclear power plant here. We wanted to get to a manageable approach to where we could start going in, we could start engaging. This is all about consent. It's all about engagement, looking at what people want, what do they not want, and being able to take in some of that information. So it started off as a desktop application. We whittled it down to 16 different sites based on objective evaluation criteria. That was based on transmission congestion, distance to interconnect. One of the factors that was in there, because it was ARPA funds, was looking at uses of that energy. What could you use that for? Well, there are a lot of places in the state that have either poor wastewater or poor water quality, and again, using this as a carbon-free way was viewed as a positive for the ARPA funds, and so that was one of the pieces that came in there. Looking at health and safety criteria, different items, noise, various different items for the interface, site development. Do you have the infrastructure around in there? Basically the environment, are you in wetlands? Is there any sort of flooding, and then basically permitting. And from that, basically came up with a score and identified 16 different communities across the state. So I don't know how well that's going to actually show up to the back of the room, but you can see there with the stars are the location of the 16 communities across the state. So if you start up we've got representation in Panhandle, Northern, Southern, Western, Eastern, trying to make sure that we had representation across all of them. So you have Rushville, Valentine, Norfolk, Sutherland, Lexington, Juanita, Kearney, Holdridge, Grand Island, Hastings, Fremont, Plattsmouth, Nebraska City, Brownville, Beatrice, and Hallam. So those are the final 16. And so what we wanted to do is, it's not saying that we're going to be building anything in any of those locations, but what we've started now is what we call phase 2. Phase 2 is actually more of a boots on the ground. In fact, it's been starting now of going out, trying to get some sort of idea to do further due diligence, based on when you're looking at a map and you're just kind of scaling, a lot of things can look very good on paper, but when you actually get out there, maybe might find out something else. So again, it's basically doing the due diligence. It's also engaging with community discussions. We're wanting to obtain feedback. One of the things that we did before we rolled out the 16 sites, we actually went and for all 16 communities, we went and we met with a group of local leaders, trying to make sure so the mayor wasn't the first person in town when he gets a phone call and hears that, hey, I just saw that they're looking at putting a plant here. We wanted to give them a little bit of advance notice. So we went through and we met with all of them, getting feedback from them of saying, is there anything that we've missed in there, being able to take any sort of input into that. All of them came through and said what they're going to need is they're going to need more feedback. And we recognize that, and that's part of the phase 2. We'll be looking at doing different ways of educating. We are partnering with the Advanced Nuclear Coalition. We're looking at using that and tapping in that resource, leveraging that way to be able to help some of the public education, not only in these communities, but also across the state. We're going to be doing site reconnaissance to confirm what we saw on the desktop, and then also start looking at, we did a qualitative on the transmission, looking at items. We're going to do a little bit more in-depth transmission study, identify issues associated with interconnect constraints. Our goal at the end of this is to narrow this on down to 2 to 4 sites that we would go. So going from 16 down to 2 to 4. We anticipate it's going to take about 12 months to complete. So that's in progress as we go. Once we get to that particular point, that's the end of the funding, and that's the end of what we currently have. However, that's not the end of the story. If we're going to be using this, we're already looking ahead and trying to figure out what do we need to do next. So this is what I call beyond phase 2. It's not part of the siting study. Some of these activities are already underway. We're already, Nebraska, NPPD is already working on technology selection process for the first SMR to be built in Nebraska. Bringing in vendors to make sure we understand what they are, what do they have to offer. We can start looking at different items to get some sort of idea and make sure we have a good match. Some of these plants will fit better in certain locations. Some of them need more water than others. So you wouldn't want to put something that has a heavy water usage in Juanita as an example. You'd want to be able to match those up and be able to look at that. So we're trying to put those pieces together. Based on that, once we get done with all of this, we look at where we're at with the progressions. One of the decision points that we're trying to target, there's an official formal approval from the NRC, for you to build a nuclear plant, build and operate a nuclear plant, you first have to have what's called a construction permit, and that's before you start any construction. You have to have that completed. That's about a 2 to 4 year process to get that completed. So obviously, if you waited to 2030, you're already 2035 before you even decide if you can start construction, and you're pushing that on out. So one of the things is you can do an early site permit. You may not know all the details, but you say, in general, this is what I want to have, and I'm going to bound the type of plants I'm going to put in there. And based on the fact that if those plants are inside that envelope, they could be placed there. What getting that completed, and again, that's about a 2 to 4 year process, but what that does for you is they're basically valid for 20 years, and they can be renewed beyond that. So now it kind of puts you into a waiting spot. That's the strategy that TVA actually used. They have one at Clinch River, and that's where probably the first GE BWR 300s in the United States will be built. They're about 1 to 2 years behind Ontario Power. So Ontario Power is probably where the first one's going to be built. They're believing that they're going to have the first ones online, and as I said, in 2028. So again, we're going to be monitoring all of that and looking at this of making a decision of spending, putting together, finding the funding, and be able to do a formal early site permit. We're also working with a lot of key stakeholders to mitigate risks to allow, to enable early adoption. So talking to some in-use customers that have expressed desire, working with various entities, government entities, working with the Department of Energy, Idaho National Labs, various different groups, looking at ways to be able to reduce the risk. Because again, that's the biggest item, all with the goal of, not with the decision that we're going to go forward yet, but all with the goal that says we want to position ourselves so that we don't have to wait till 2030 when we're going to start doing some of this planning. So talk to the Department of Energy, Idaho National Labs, NEI, which is, and also the state of Nebraska. And then also exploring potential partnerships of other places where we would be able to go with that. So there are a lot of activities that are that are out there that are being done as baseload. Some of these others, if we got into something like an early site permit, that'd be a more formal process, because now we're talking about having to fund several dollars. We're trying to do all this, manage the risk, and not to be able to, you know, if you put all this money into it and it comes up that something falls short, you know, all of that has to be recouped into rates. We don't want to be doing that. We don't want to put that risk on the backs of our consumers. So that's the effort that we currently have and where we're currently going. And with that, I wanted to leave some time in case there was any questions. So.
Okay, let's open it up for questions. While we're looking around for those, Dan, in the wind and solar world in certain counties, you start to see pushback from county commissioners on, you know, the not in my backyard. Have you seen anything like that in these 16 communities, or what's the feedback so far regarding new nuclear in some of these communities?
So it's an excellent question. For all the 16 communities, when we initially did all of the, what we've gone out, we have a website that's out there that actually, we've been aiming this at trying to make sure we get information out to everybody. We've gotten positive feedback through all of it. It's been very enthusiastic. There's naturally some questions. There's some things that they want to have from some education. But again, you know, that's something that we expected that we're going to end up having to do. That's just part of due diligence. We did develop a website, nextgenerationne.com, that is available. You can go out there. It basically gives you some background information. We've gotten and we've used some of the local stakeholders from around Auburn, you know, the communities and around Nebraska City, Peru, and that area that have grown up around Cooper, to try to help them a little bit, have them some sort of idea of what's it like to grow up around a nuclear plant. Do they think it's safe? Do they believe, what do they see as the advantages? What do they see as the disadvantages? Trying to just put this information out there. But again, it's been very, very positive. We have gotten a lot of different feedback in via, there's text ways of being able to provide feedback. Overall, I would say the overwhelming majority has always been positive. There's been a few that have expressed some displeasure. We understand that. But again, it's a way of keeping the communication of going open. We have not identified anything on any of these 16 communities that would say that that they don't want it there as of yet. So no decisions made, but still going forward. Willing to go forward with the process.
Okay, questions? Yes, sir.
Two come up right away. With a small nuclear reactor like this, what do you do with the waste? And then what about the possibility of somebody, getting the materials into their hands, terrorists, for example?
Sure. Both very good questions. When you're looking at, I mentioned that some of these reactors, some of these advanced reactors, are actually able to take some of the existing used fuel that we currently have. We're changing our terminology a little bit when we're talking about it. Like the fuel currently for all the existing conventional plants is all being stored on site. We have a contract with the DOE that they're working very hard at coming in to be able to comply, to be able to take that. They are in contract to take that fuel from us to a storage facility somewhere. They're working very hard to have that completed by 1998. A little bit behind, but in the meantime, we're storing it right there on site. So we have a storage facility that's there. It's built, it has pylons that actually go down into the bedrock, so it stays there. It's right around the individual sites. They're all very passive. They require no electricity, just like small modular. It relies on the fact that hot air rises, and so they have little openings in the bottom that allow cooler air to come in. Any sort of the heat, when you're looking at it, we maintain that so that it always stays within about 10 degrees of ambient temperature. And that's just all done naturally. It gets a chimney, goes through, and there's holes out to the top to carry the heat away. The only thing that can really go wrong is if you get animals that build nests or something in there. So, we have to do examinations, make sure we're monitoring, obviously, for temperatures at all times and making sure all that. But they're perfectly safe. Those facilities were at Fukushima that went and experienced the tidal wave that came in, the tsunami. Stayed there, they were perfectly fine. They've done examinations of them and there's been no damage to them. They're designed to be able to operate under 50 feet of water. So again, they're very robust design, very passive designs. So they're currently stored there until they get to a storage facility. However, when you look at that, instead of calling that waste, we're actually starting to consider that more of used fuel. When we burn, like at Cooper, for example, we take the available energy that's in there, we only use about 10% of that. So 90% of it is still there. So they are currently looking at, like they do in France, of going through fuel reprocessing, be able to minimize down the amount of what you truly have as true waste. They can take that fuel, and for every 8 bundles, they can come out with 2 new bundles. So again, it's a fairly good way of being able to extend that out. That reduces down the volume. If you look at that total volume, you may think, well, boy, 50 years of operation, there must be piles everywhere. If you took all that fuel and put it all into one location, it would fit on a football field size, about 10 foot high. So very heavy, but very compact also. So it's heavier than lead, so it gives you some sort of idea. But again, it's built in to make sure that it's being very, very safe. Some of the new plants are actually looking to be able to take some of that fuel, be able to use that fuel as part of their source fuel as they go forward without doing the reprocessing. So again, there's various ways of looking at the fuel structure of going through there. There are groups that are looking at, and the Department of Energy is looking at it also. We were originally going down in the United States in the early 70s to do fuel reprocessing just like what France did. It was decided, Jimmy Carter was concerned about proliferation of getting into the hands. And so what was decided was, no, we're not going to do it. We're going to keep it stored there. When you look at it, they're protected inside these concrete casks from missiles, tornado-generated missiles, it's thick rebar. So again, very well protected to be able to make sure that no one would be able to get there. All of that is being built to be able to increase the safety factors of what we're doing. Looking at that fuel, being able to use that fuel for the future use. So again, it reduces that down. If we were to take just the existing used fuel stockpiles, it would power all the plants that are currently online, all 94 of them, for 150 years. So it gives you some sort of idea of what you'd be able to do. Cost is a little bit different. You asked a second part, which was security. So for most of these advanced nuclear reactors, they're actually built mostly with the reactors are underground. Because again, they're looking at hot air rising, gravity always wins. So they're wanting to put them down below so that they have water sources and other things that can flow down to them. So that basically prevents anybody from coming on in. Some of the plants, while every single plant currently that's licensed by the NRC has a security force there to be able to guard and be able to protect, just like what they do at Cooper, they're actually looking at some of these, especially some of these mobile units, if it's in the back of a truck, to be able to minimize that on down and say that they can't get to it. For them to get to the fuel, to get to that particular piece, they basically have to disassemble the entire reactor. So it's been built such that it already has its protection built into there, so somebody can't get in and get some of the material and be able to get out. Does that answer your questions? Okay.
You know, we are over time, but we'll have one more quick question.
Do you have cost per megawatt estimates or targets that you're looking at?
There are a variety of those that are out there. A lot of them are very early at this particular stage, so they vary dramatically. Most of them are based on first-of-a-kind costs, which would probably not be competitive in today's market in any sort of fashion. Give you some sort of idea of where some of them are targeting at. Some of them are targeting to be believing that they can be compatible with natural gas power eventually when you get to it, when you look at a levelized cost of electricity. But again, the initial part, you're probably talking about for construction costs, you're talking around about $1 billion. Just maybe a little bit shy, 900 and some million, but again, it's in that target range. A lot of it goes on what they're going to require on the O&M and what the staff size they need to be. Cooper, the biggest item of Cooper, it's very low. It bids into the market, and its variable cost of energy is very, very competitive. However, it's fixed cost being able to recoup all of those. And so one of the things is the biggest fixed cost is we have 650 some people working at Cooper on site. Well, this starts lowering the footprints down to 200 to 300, and so now that starts changing some of those dynamics to be able to go out there. So I can get you different numbers of the various different ones, but I don't have anything that can say where they're going to go. They do believe that they'll be able to see from a first-of-a-kind costs, dropping that down by roughly by at least a half to 2/3.
Okay, very exciting, very informative. Thank you, Mr. Buman. Appreciate it.
Thank you.